Hi, good morning. This is my third attempt at recording this. Polar graphs, the polar coordinate system can be confusing. That's why it's taking me 3 recordings. I don't want to try to make this as clear as possible, but it can be confusing. If you have to watch this video 3 times again, know that it took me at least 3 times to record this. This might just be I might have just lost count. I don't know. Who knows? Alright, so a lot of what we say should be a review of pre-calculus. But again, because of how confusing it is, your pre-calculus teacher might have taught it differently. That's fine. If this hopefully just knocks something loose and makes you go, oh yeah, okay, I remember seeing that. That's good. If this is your first exposure to polar coordinates, you might need to watch this more than once for sure. You might want to come talk to me about it in person. Okay, full stop. Use the polar grid to plot these polar points. Rahul once said to me, "Isn't it clear that these are polar points?" And you should all scream, "No." It's not clear that these are polar points because if you forgot all of the polar stuff you ever knew, and I asked you to plot this point, you need to be able to do that. You need to be able to plot this point in a rectangular coordinate system. Now, I've used the words rectangular coordinate system before, I think in 9-1. What I mean is your standard coordinate system, where this is an x coordinate and this is a y coordinate. If that's an x coordinate, it means go 1, 2, 3 along the x-axis, and pi over 6 y coordinate would mean go pi over 6 up. That would be about 0.5, 3 over 6. So 1, 2, 3, 0.5 up. That's a rectangle. Straight, straight. Maybe it's left, down. Maybe it's left, up. But those were the rectangular coordinates that you were molded in. That was your foundation mathematically. Those are the standard systems we used. Just like with parametric, and this lesson will have very, very similar stuff to parametric, but also a little bit extra. Just like with parametric, the reason we're going to use polar is because all of a sudden new things become functions that weren't functions before. These will make a stunning return in multivariable calculus, so if you're planning on taking that course, if you're planning on being an engineer, make sure you pay attention in this lesson. And when I say stunning return, I mean like it's taking a whole extra level in 3D. Okay, so the idea of a polar coordinate is that it's graphed in terms of a radius instead of an x and an angle instead of a y. And there's 2 ways to think about this. The first way is to treat the radius first. The radius first would be 1, 2, 3 away from what you would have called the origin. In polar, we're going to call it the pole. Get it? 1, 2, 3 away from the pole, and then rotate pi over 6. Now, how are you going to rotate exactly pi over 6? Isn't that a judgment call? Well, these guidelines are telling you angles, and these circles are telling you radii. So this is a pi over 6 guideline. This is a pi over 3 guideline. How do I know that? Well, it's 3 even sections of pi over 2. You need to know that angle is pi over 2. Pi over 2 divided by 3 is pi over 6, so each of these should represent pi over 6. You can see it with weirder divisions, but that's a little weird. Get it? So, one option. 1, 2, 3 away from the pole in the positive x direction, and then rotate pi over 6 up. And now I found point A. Last year when I tried to teach radius first, I had like a insurrection on my hands. So if you want to do angle first, that's fine. Pi over 6. You find the pi over 6 guideline first, and then you go 1, 2, 3 away from the pole. Works out fine. I'm going to do it first for B. So here again, the angle method. The angle method would be going the angle first. So where is the pi angle in this grid? Not grid, obviously. Sorry. in this plane. Pi away from, we're always starting here, is this line. So I go pi away, I rotate pi, and then I go 4 away from the pole. 1, 2, 3, 4. That's B. And again, no harm, no foul if you want to do it the other way. 1, 2, 3, 4. Rotate that point 180 degrees, pi radians over to here. I'm sure some of you are like, ooh, he said degrees. Ha ha ha. All right, C. Just to mix it up, we can go radius first. Let's do the radius first this time. 1, 2, 3 to the right of the pole. And then I rotate it negative 5 pi over 6. That means now I get to go clockwise for once. So negative 5 pi over 6 clockwise from here would be pi over 6, 2, 3, 4, 5 pi over 6. Now I lost the guy then. Yeah, right here. Negative 5 pi over 6. If you want to do the angle first, again, 5 pi over 6. You're still going from this, negative 5 pi over 6 would get you to here, radius 1, radius 2, radius 3. Okay, this last one is the one that's confusing to people. So here's the angle method first. The angle version of D would be to go 3 pi over 2. Where is my 3 pi over 2 line? You should all know this by heart. It's the negative side of the x-axis. But now the radius is negative 2. That's what makes this the point. That's what makes this the hardest one. So I'm on this side. And now you want to go negative 2. That means instead of going down the angle we're on, or along the angle we're on, we're going to go backwards. So I go up 1, 2. Okay? And that's why it's confusing. So there's D. If you don't like that, you can do angle, or you can do radius first. Here's the radius first method. Where's negative 2? Well, this is a positive 2 radius. The negative 2 radius is here. And then I want to rotate this 3 pi over 2 in the counterclockwise direction. A lot of people want to go clockwise for some reason. Counterclockwise direction. Positive angles counterclockwise. Pi over 2, 2 pi over 2, or pi, 3 pi over 2, and you end up here. I think that's easier. Like I said, people were not happy with this last year. But there's D. So you can do the radius first, you can do the angle first. I don't really care, as long as you get it right 100% of the time. One more time, negative 2, positive 2, negative 2, and then rotate it 3 pi over 2. Or 3 pi over 2 would take you to here, but then you're going positive 1, positive 2, so negative 1, negative 2. However you want to do it. Enough said, I hope. Can be confusing. Sorry. It's just, that's what's hard about teaching this pre-calculus stuff, guys, is that a lot of you have seen it different ways, and you get confused because I'm showing you new ways, different ways, unfortunate ways. Oh, math. Okay. Rectangular. You need to be real careful. Pay real careful attention to when they say words like rectangular and polar. Rectangular, again, means we're giving you x and y. So I go back to my coordinate plane, good old-fashioned coordinate plane. Negative 1 on the x-axis, root 3 on the y-axis. And you want to make a triangle, just like when you were doing trig. Just like when you're doing basic trig. I don't know why I made that so small. There's no reason for it. You guys can see no matter where I draw it. That's why I made it small, so I can actually draw straight lines. Okay. Negative 1, root 3. Okay, so I have that basis for a triangle, and this is asking me to find the radius if it was positive and find the angle if it was positive. Guess what? The radius side is easy. The radius side is easy. That's just the hypotenuse. What's the hypotenuse of this triangle? -1 root 3. You should have it memorized. If you don't have it memorized, you can use Pythagorean theorem. You shouldn't have to. You should know it's 2. Similarly, when we're asking, okay, so it was 2 away from the origin, 2 away from the pole, how far did I have to rotate this line? That's theta. To know that, you need to know what angle's in here. And again, you should have that memorized. You should know what kind of angle produces a 1 root 3, 2 triangle. What angles across from the root 3? It's pi over 3. And what angle is opposite of the root 3? It's pi over 3. What angle would rotate me until I'm pi over 3 away from pi? Pi minus pi over 3? 2 pi over 3. So my radius was 2. My angle was 2 pi over 3. Okay? However you want to get it. If you're like, oh, but I know that angle. That's what... I forget if it was Francis or not, but someone was like, what if I just know it? Sure, that's another way to do these problems. You can just know it. Pi minus pi over 3. One way. Count by pi over 6. Another way. I don't know. Alright. Now, this is saying, okay, keep R positive, but I want to know what would happen if I had gone the opposite way. If I had gone clockwise. How far did I have to get to that angle? And this is actually easier, I think. Radius is still going to be 2. Matchy, matchy. We're still 2 away from the pole. But what would this rotation have been? Pi plus pi over 3. 4 pi over 3. Ta-da! Okay. Now the fun one. So, this is why I had to stop recording the last time. I think I messed this up. So, let's talk again. I'm going to clean up the picture, or by clean up the picture I mean just redraw my triangle. That's probably a little more accurate of a representation of this triangle, because now it's taller this side than it is that. Anyway, so that's still 2, but now I want it to have been negative. Okay, spoiler alert, it's definitely going to be -2, okay? These are both going to be -2. But we're asking, what radius would I use, what angle would I use if that was the radius of -2? So, here is the radius first method. The radius first method would have said, oh, -2 to start would have been 1, 2 this way. And then now I want to use a positive theta. So if I was 1, 2 this way, and I wanted to rotate it until I got to here in a counterclockwise way, how far would I have gone? How far would I have gone with that angle? And I think you can see pretty clearly that that would be pi over 3 away from a full rotation, or 5 pi over 3. If you aren't sure what I mean by when I said count by pi over 6, pi, 5 pi over 6. So pi, 7 pi over 6. So this pi is 6 pi over 6. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6. Pi over 6. Okay, 5 pi over 6. The angle first method, I think, is a little harder here. So we're saying, what would I have to have rotated so that this would be counting backwards by 2? And then you would have to look at the dual radius. Let's call it that, the dual radius. And you would have had to say, well, how far would I have rotated to get there? You would again see, 5 pi over 3. It's the exact same angle, just starting from a different spot, from here. And then you would have counted backwards 1, 2. I think that's a lot harder. But either one of those needs to make sense. This is very hard. You know it has to be a pi over 3 reference angle. I guess I can say it that way. I'm going to clean that up a bit. Or, no. I'm going to redraw it one more time. Maybe this will help. So let's use pink. So now I want the radius to be 2. Wow, that's a great triangle. I want the radius, like I said, it'll still be -2, okay? It's either going to be positive or -2 as soon as you draw it. It's not ever going to change magnitude, only change direction, sign. Negative radius, stupid. Negative radius, negative angle. Negative angle, again, the radius method. Here was 2, here was -2. And you wanted to rotate that negatively to get to here. How much of a rotation is it from this axis to that? What was the size of that angle? That angle was, like we said back here, it's still pi over 3. It's pi over 3 in all of these triangles. That's why all of the angles have a pi over 3 in them. So to go from here to here, it would have been a rotation of -pi over 3. Angle first method. You want to get to here, you have to go -pi over 3. And then you count backwards 1, 2. However you want to think about it, I'm so sorry if you have to watch these 2 slides more than once. I'm sure it'll take a long time in class to explain it. Alright, now the easier ones. Alright, the conversion equations. These conversion equations are just based on trig. They're just based on trig. So, let's look at this. I'm going to draw all my stuff right here. This would be x, that would be theta, that would be y. We just did this in the last example. I would call the hypotenuse in this case r. That does represent how far this point is from the origin. The distance from the point to the origin is the radius. I guess I should have mentioned this. Polar, we're thinking of circles. That's why we're talking about radius and angles. We're going to talk about circular coordinates, sort of. All right. So, x squared plus y squared equals what? I'll give you a big hint just by drawing this. Oh, r squared. Good. Tan theta, in terms of y and x, in terms of x and y, guess what? Opposite theta, y, adjacent to theta, x. Y divided by x. Okay, x in terms of theta and r. That's the hard part. Which trig function would relate x and r? Adjacent, hypotenuse. R cosine theta. I guess I'll write it out. Cosine of theta in this triangle would be adjacent over hypotenuse. Similarly, sine theta in this triangle would be opposite over hypotenuse. So that's r sine theta. You will need to have memorized these four conversion equations. You don't really have to. You can just draw this triangle and have it like that. So change this point to rectangular form. Two methods I want to talk about. Method 1. All right, really quick. What form is it in? It's polar, because I'm trying to change it into rectangular form. So method 1, if you're good at polar coordinates, is to picture what this would look like. 2 out, and then rotate by pi. Or rotate by pi, and then go 1, 2 out. Either way, you get to here. Because it's 2 out, rotated by pi, or rotated by pi, 2 out. So what coordinate is that? -2, 0 in rectangular form. Method 2. So obviously method 1's faster, but you have to be able to graph really quickly on the fly. Or picture it in your head. Method 2 will be to use the conversion equations. So x equals r cosine theta. That's r and that's theta, just to be clear. Which equals, cosine of theta is -1. 2 times -1 is -2. Y equals r sine theta. Sine of theta is 0. 2 times 0 is 0. So x is -2, y is 0. That's it. Not that bad. Not that bad. Let's do method 1 in the lighter blue, I guess. I don't know. So what form is this in? We're going to change it to polar form. So this is rectangular form. Again, don't rely on just seeing the pi. That's not good enough. This has a meaning in polar coordinates. The angle is 3. I know you don't like thinking about that, but that has a meaning in radians. 3 radians is huge radian. It's like almost pi, right? So method 1, you draw the triangle. Because it was rectangular coordinates, you know that's 3, -3, that's +3. So my radius is what? Some of you might recognize that this is an isosceles right triangle, that this is 3√2. Again, you could use Pythagorean theorem. Method 1 is not for people who don't know their trig. Not for people who don't know their special right triangles. Okay, and then this angle, if it's a special isosceles right triangle, if it's a 45, 45, 90 triangle, if it's a 1, 1√2 triangle, the angle here is pi over 4. So the reference angle, the entire angle would have been, the reference angle is pi over 4. So this angle would have been 3 pi over 4 to get the negative x and the positive y. So the radius is 3√2. Gross, sorry. And the angle is 3 pi over 4. Like I said, I don't necessarily recommend method 1, but it's way faster than method 2. And does not require memorization. So method 2 here. Okay. R squared equals x squared plus y squared. So we end up doing the same work. Again, that's not work for me. I know it's 3√2. R squared equals 9 plus 9, 18. So in the AP test, sometimes you wouldn't have to simplify that. Most times you would until you got to 3 root 9. And then tan theta equals 3 over negative 3. Tan theta equals negative 1. Careful about arctan. Arctan of negative 1 is negative pi over 4. But this angle would not be negative pi over 4, I assure you. So you need to think carefully about how you would have basically this situation where x is positive, y is where x is negative and y is positive. Okay? And what angle would that have to be? You have to think carefully because this has many solutions, or at least it has 2 solutions, right? This has 2 solutions. One of them is what you want. One of them is not what you want. So don't just apply arctan. I'm not using a calculator for any of this. Don't just take arctan. I'm going to write it down in a second. The correct theta, I'll just say there's 2 solutions to theta. There's 3 pi over 4. I wonder if that's right. And the other one, where tan of theta would be negative 1, would be 7 pi over 4 in quadrant 4. I don't want that one because x is negative, y. So you get 3 root 2. So either way you cut it, this requires thought. This requires a lot of thought. Careful, guys. And here, the bigger note, careful. If I want to do theta equals arctan of negative 1, I would get equals negative pi over 4. But this is wrong. It's still the right reference angle, but this is totally wrong, right? We're looking at this picture. And we would want this equivalent version of it. So don't just use arctan. Don't overuse it. Careful. Okay, equations, conversions, the other way. Sorry, not the other way. Equation conversions. Okay, what shape is this? You should have all said a horizontal line. It's a horizontal line, whatever. How do I do equation conversions? We use the same conversion equation table right here in your notes. So y can be replaced by r sine theta equals 4. And now you want to solve for r in most cases. Okay, unless they say otherwise. So r equals 4 over sine theta. And that'll be good enough for me. You could also reason that 4 over sine theta is 4 cosecant theta. Rectangular polar here. Replace x with 3r cosine theta minus r sine theta, because y is sine theta. Plus 2. Sorry, it looks so ugly. Alright, now this is really hard. I'm going to first move the negative 2. Our goal to solve for r would be to factor out the r. I can't factor out the r until I get the negative 2 to the other side. So 3r cosine theta, and I'll be able to write it prettier, minus r sine theta equals negative 2. R times 3 cosine theta minus sine theta equals negative 2. So r equals negative 2 over 3 cosine theta minus sine theta. Okay, so just to point out to you something that's pretty absurd going on. What graph was this? A horizontal line? Look how complicated that equation is polar-wise. What graph is this? Guys, it's a line with a slope of 3 and a y-intercept of 2. Craziness. We don't use polars to graph lines, that's why. What kind of graph is this? Oh. And now you see the funny side. Don't worry, I'll talk about what it is. X squared. I'm going to replace it with r. Okay. Yeah, slow way first. R cosine theta. This is the slow way. But there's no shame in doing things slow as long as we're getting it right every single time. I'm going to shrink this stuff. I'm going to move this over a bit. Minus 2 r cosine theta equals 0. R squared cosine squared theta. This is a really slow way. You should have noticed something. But I'm going to show you that it's okay if you don't notice it. Okay. Let's just say... what do I want to do? Let's say I worked it out in R. I have R cosine squared theta plus R sine squared theta minus 2 cosine theta equals 0. Okay, so that leaves me with two options. Either R equals 0 or R cosine squared theta plus R sine squared theta minus 2 cosine theta equals 0. What's going on here? This is a degenerate solution. It's the graph of the point. It's the graph of the pole. It's one of the graphs of the pole, let's say. That's why it's called the pole. It's because it has crazy solutions. It's a dot. Let's talk about what this is. This should be a graph of a circle. Not a circle like this, but a real circle. What's the radius of the circle? It's not actually 0 if you completed the square and did everything parametric. Did everything in the pre-calculus, oh gosh, what's it called? Conics way. There we go. So that's not the right circle. The radius of this circle is not 0. So we stick with this solution. Now, you're all going to hate me when I show you the real way to do this. Plus r sine squared theta equals 2 cos r times cosine squared theta plus sine squared theta. And now you might see it. Because cosine squared plus sine squared is 1. That's the Pythagorean identity. That this is 1. And so that's the right answer. How could you have gotten there a lot quicker? Quacker. Wow. Alright, so here we go. How could I get there a lot quicker? If you look back at your conversions, x squared plus y squared is r squared. It just is r squared. So you should always look to see if you have x squared plus y squared, because that is r squared. minus 2r cosine theta. You factor out the r. You still have to do the thing we talked about just now. We have to say r equals 0 is not possible. R minus 2 cos equals 0 is possible. R equals 2 cosine theta. So that is a nice circle graph. Equation conversions the other way. Polar to rectangular. What is this equation? This is a circle of radius 2. Okay, you don't need to know that, but it'll help you get your answer. How do I convert this? Usually I want to square both sides so that I can get r. So I can get r out of there. Because r squared is something I know. R squared is something I know. I will also try to look for any time I can get r cosine or r sine. Okay, so we're looking for r squared because it equals x squared plus y squared. R cosine theta because it equals x. And r sine theta because it equals y. We want to get rid of x and y. Or sorry, we want to get rid of r and theta until they're gone. Okay. So in this case, the first one, there really is no other option. You don't want to multiply both sides by r because you'll end up with r over here. I just want to square both sides. I'm just going to go straight through and square both sides. So I get r squared equals 4. X squared plus y squared equals 4. And you don't have to solve for y. That's the correct equation. This is a circle with radius 2. Done. Squaring both sides here won't work. So you can replace the r, but you won't be able to replace the theta. That's not good. Instead, here I'm going to multiply both sides by r. Multiply across by r. So I get r squared equals 3r cosine theta. And that's the important part. Because now that I have a cosine theta over here, I'm going to get r sine theta. Sorry, r cosine theta will get rid of the theta. R cosine theta is x. X squared plus y squared, r squared. R cosine theta, x. Good enough for me. Stop there. Last, let's use pink. Cosecant theta is a problem. So one thing that's helpful to do is to write cosecant in terms of sine. Squaring both sides is the same problem over here. Multiplying by r, you don't know what r cosecant theta is. However, if you make the connection that you can write 2 over sine theta, now I would cross multiply both sides by sine. R sine theta equals 2. What's r sine theta? Y. Alright, I'm going to stop the video here because I feel like I've been recording for a long time. I think this is only a half hour. People are going to start coming in. This is a good place to stop too, because it's about to get a little more fun. So I'll talk to you later. Make sure you try the simple problems on 9-2, the ones that are just conversions. You should be able to do all of the conversions now. Anything that asks you to sketch a polar graph, wait till you watch part 2. You probably have time to watch part 2 now. This was a short video. Anyway, thank you for your hard work. Make sure you do the assignment. You will fail the AP test if you aren't doing the assignments. I'll talk to you later. You guys have a great day. Bye-bye.